Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show. Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers, because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems, because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. My guest is Giovanni Strona. Giovanni is a senior researcher at the European Commission. We're going to talk about his current work there and perhaps his past work with ancient pathogens. So welcome, Giovanni.
Thank you. I'm very glad to be here and to have a chance to talk about my recent research.
Well, tell me about your current work, with the European Alliance. What are you doing there?
So I'm working for the Joint Research Center, which is basically one of the directorate of the European Commission, and its mission is that of providing scientific advice to policy makers in Brussels, and we are doing different kind of research. So there is quite a bit of topics there. So I'm a macroecologist, and I'm working in particular on the effect of global change on and the role that ecological interaction play in global change and biodiversity loss in general. So I've been doing that for the last, I would say, 10 or 15 years, and I'm still doing that at the...
Right, but what research questions are you looking at? Are you dealing with ancient pathogens coming from permafrost, or was that before? Like, what's your...
Oh, yeah, that was sort of a self-contained project that I started when I was working at the University of Helsinki a couple of years ago. And it was mainly born from the fact that in the past I've used the same kind of simulations that we are using in this research, which is artificial light simulations. And at some point we figure out that with that kind of tool, you can actually take organisms from early stages of evolution of communities and move them into modern communities. And then we thought that there was a lot of parallels between this potential experiment and what is now going on with the permafrost melting at an accelerating rate, and a lot of potential of organisms which are potentially released into the environment. So we put together like possibility of doing that in these kind of experiment simulations with the fact that there is a lot of speculation on what could be the effect of those ancient organisms coming in contact with modern communities.
What do you mean? What organisms? Where? And what effects do they have?
Well, we actually did. So we did not look at a specific organism. So the tools that we use, these life simulations, are basically systems which provide analogies to real world system, in particular like with microorganisms, bacteria, and viruses. but there you have like computer programs that evolve from starting from simple ancestral organism, which can do just very simple operations. And basically this program mutate and reproduce and interact with an environment which is made up of numbers. And by crunching numbers, they have access to energy, and they compete with other organisms, and you can have pathogens there. So it's a system that it looks quite abstract and far away from the real world. But even though these like digital organisms that you have there not correspond like biological terms to any specific bacterium or virus that you can have in the real world, what it matters is that the ecological processes that you see in place there, so the way these bacteria interact with other bacteria and with viruses, are mimicked quite closely in a quite realistic way what you can see in the real world community. So we thought in the real world system now we have with the permafrost mapping we have a huge number of, as I mentioned, of organisms which are breeding, and this number is as high as 4 sextillion of cells of bacteria and viruses which enter the environment just in the northern hemisphere each year, which means 4 per 10 by 10 at the power of 21. So it's a number of higher than all the stars in the galaxy. So it's a huge.
But what pathogens are in the permafrost? What has been sampled and observed? What's there and where?
Yeah, well, the fact is that we actually there are studies that have looked and that have managed to isolate different kind of viruses and bacteria which are like very far away from the model ones and very different. So there are, but there is no like we cannot say that they cannot find necessarily viruses that correspond to that can cause particular disease or that are identical to the model one. Even though there were examples, for instance, where you had like anthrax, some cases of anthrax from carcasses of animals in the ice, but that's of course we are talking about like more recent pathogens that came in contact with the model community. As far as concerns what can come from the permafrost, the problem is that we actually do not know, and that's why we actually made this study. So there is so we know that there's a lot of microbes that are trapped in ice, and there have been a lot of studies that not a lot, but quite a few studies that have tried to revive some of those organisms in laboratory conditions, and it has been shown that at least some of these organisms which have been trapped there for millennia will be viable. And I'm talking mostly about bacteria and viruses, but like there was, for instance, one study that was published basically the same day that our paper about time traveling pathogens was published, where in that study they were actually able to revive an ancient nematode from the Siberian permafrost, and that nematode was 48,000 years old. And a nematode is a multicellular organism, is a roundworm, so it's even more complex than bacteria and viruses. So there is the possibilities that all this diversity which is trapped in ice is not just they're dead, but can also come alive again when the permafrost melts. So the first question we have to answer there is not necessarily whether there is like a new coronavirus trapped there or something that we might fear, but also whether or not this organism could survive in the model communities. And that question is not just about reviving things in a lab, but it's also an ecological question, because of course if you are a pathogen, you need to find a suitable, immediately suitable host, and then you need to reproduce to a degree which permit you to survive, not just as an individual, but as a population, and to persist in the communities. And today there has been ours was the first study that tried to tackle this problem, this question directly. So, and we actually found that surviving for this organism in the modern community is quite a common thing. So even though those organisms are ancient and are somehow separated by a long evolutionary and co-evolutionary time from the modern host that they can infect, these ancient viruses can survive, can find a place, can reproduce, can stay into the community. But that the second question is, if these organisms are able to survive, what could be their impact? And before like jumping to what could be like the impacts for human health or also for like producing outbreaks, which was of course one of the one question that the media were quite interested in. The first question is whether they could have some ecological impact on the microbial community that can invade. And we found that also this is quite rare. So in 3% of our simulations, those pathogens became dominant in the modern community, so they became more abundant than the modern virus.
What kind of pathogens and how would they be picked up? Would they volatilize in the air? I mean, have you tried to culture any of these pathogens? Like, what are they in addition to modeling?
In our modeling, you mean, or in the real world? So what
have you been able to sample and look in the real world and see? Again, what strains are there? I mean, there was
no. I mean, our study was just modeling study, so we did not take any samples. So we was just, so our simulations are somehow limited to our in silico system. There are other studies where by other scientists where they have tried to isolate those, like as I said, viruses and bacteria and also other multicellular organisms from trapped in ice and the permafrost. And sometimes they found something interesting, like they found the giant viruses, for instance, so viruses very different from the modern ones, also from a morphological perspective. But as for our study, as I said, our main goal was that of looking at the ecological mechanisms which can determine whether or not these organisms can survive. And as I said, we did that not by using the real-world organism, because that would be actually unfeasible or very difficult to be done in the real world. So to give you some numbers, so what we did was we simulated 100 different environmental settings with different amount of resources, which might mimic like different kind of environmental scenario with more or less resources available for those microorganisms. And then we simulate 100 replicates for each one of these 100 settings. And in those replicas, we let evolve our communities of digital viruses and bacteria for 100,000 of generations, and we obtain sort of the corresponding a corresponding time of evolution in the real world of hundreds, thousands to millions of years of bacterial evolution. So this is something that you couldn't do in the real world. So potential experiments that.
No, but if you start with knowing what strains or species are there and what niches they occupy, maybe some have to live in an anoxic environment under permafrost, and some are more aerobic, and some require permafrost or organic material in the permafrost in order to live as a substrate, and some not. And it seems like
I mean I see what you're saying, but it's not exactly the so when we think at organism, and this is exactly what I'm doing in most of my research, not just in this specific topic. It is not just so you can, for sure, you can take a single organism and you can look at what are its requirements, its ecological needs, and you can determine whether or not it might be able to survive in certain conditions. This is something that, like, when scientists try to revive this organism in laboratory, they have also chances to explore what would be the conditions most favorable to survival of this organism. But that part is not what determines the whether or not it's in the real world. The ecological niche of one species is of course important, but it's sort of the minimum set of conditions in which the species can survive. But then whether or not the species will be able, like a pathogen, will be able to be successful or to spread or to spill over to other species or create big outbreaks, is not just the results of the features of the pathogen, but it's the results of how the features of the pathogens interact with complexity and the diversity of the system in which that pathogen lives. And in this very peculiar setting where we have ancient pathogens which are released from which came in contact with modern communities, and where there's been a very long-term evolutionary isolation between the pathogen and the modern community, then the main question is not about which condition could permit which environmental condition could be favorable to the survival of the organism, but is related to how the organism, the ancient virus will cope with the modern organism, and it's specific, and most importantly, in terms of the relationship of immunity between the host, the pathogen, and the host. So you can have different scenarios where you can imagine a scenario where the modern host have been separated for enough time from the ancient pathogen that they have lost the immunity that they might have developed in the past towards the same ancient viruses. And in that setting, those hosts might be actually very vulnerable to the ancient pathogen, and so the ancient pathogen can then thrive and maybe kill the modern host and create big damages to the modern communities. But you might also have the opposite situation where, since these modern pathogens have been already exposed throughout their evolutionary history, of course, to the ancient viruses, they might have already sort of developed immunities towards them. So in that case, they might still have defenses, and that would prevent the pathogen to...
Right, but we have zero idea. Yeah, what in the modeling, do you have an organism? Do you have a pathogen? Or what is the modeling just purely mathematical? Or what does it look like?
No, exactly. So that's the point. The kind of simulation that we use is quite peculiar in that it's not a mathematical model or a simulation where you have to make a lot of assumption, or you have to tune like parameter where I have to decide how an ancient pathogen will interact with the food, or what will be the immunity of the food pathogen. So what you do with this artificial life simulation is so you have a set of like initial basic rules which just determines how like the organism interact with the environment, and how the organism mutate from so you sort of define proteobacteria, let's say an ancestral bacteria, and then you just let these bacteria to evolve under certain environmental condition. But then what you do is the equivalent of what you would do by putting a bacteria in a petri dish and just let the bacteria to reproduce for a long time. Then at some point we introduce in those virtual petri dish, we also introduced some pathogen. But the reasoning was the same. So those pathogens simply multiply and evolve freely. So the rules that you set are like correspond to the rules that natural and genetic evolution have, but all the rest that you observe in terms of ecological processes and the evolution of immunity, and eventually the loss of immunity by the host, or the extinction of species and the emergence of complexity in those communities, are all emergent properties that you do not control, you just observe them. So what we did was setting up this experiment and then letting them develop. And in those experiments, so try to explain them. We started with one ancestral virtual bacteria and one ancestral virtual pathogen, and we let them interact and evolve. And those bacteria and pathogen differentiate throughout evolution into different species and make and create in the end complex communities with a lot of different kind of bacteria and a lot of different kind of viruses. And as I say, we had not control on how those communities evolve. It was sort of a natural process similar to what you would obtain if you had hundreds, thousands of years of experimenting in a petri dish. And then at some point, and of course, since you run those simulations in the computer, you are not controlling what happened, but you can record information and store information at every single time step. So what we could do in the simulation was coming back to community in the past and pick up some of the ancient organisms and transfer those ancient organisms into the corresponding modern communities that we had evolved. So this is the kind of experiment that we did. We evolved for a long time those communities, and then at some point we pick up some of the ancient viruses and we move them into the modern communities. And again, we did not make, we just sampled random viruses, random ancient viruses, and we put them randomly into their modern community. So we really simulated as close as possible, of course, in our simulation, what could happen if you have like the permafrost melting and some random virus from the past at some random moment coming in contact with some modern communities. And again, then at that point, we tried to look at what was the effect of those mix-up of ancient viruses in the modern and the modern organism in ecological terms. So again, since we were simulating things used in the computer, we could run in parallel simulations where we actually move the organism from the past communities, the viruses from the past communities to the modern ones, and those we can call them the invasion experiments, and control experiments where we let the communities to continue to evolve without any intervention, so without any invasion of viruses from the past. And by comparing these layers of control experiment with no invasion and the experiment with the invasion, we were actually able to quantify the potential effect in terms of the observed difference in diversity in the communities where we had the invasion of the virus compared to the community where we had no invasion. And what we observed at the end of those experiments was that in most cases, there was not much difference in the control experiments compared to those where we moved the invader, but in a few cases, we had actually quite dramatic changes. So the diversity of the experiment where we had the invasion of viruses from the past was in some cases 30% less than the diversity of the control experiment. So in those cases, a single ancient virus strain reduced the diversity of the microbial communities by 30%. Yeah. So this is what we did.
Okay. All right. I got it. Okay. So where is the modeling going to go from here then? How is this going to get used in the real world?
So what kind of inspiration you mean we can take from these results to set up a real world experiment? Is that the question?
Right. Or what would be a change made based on these results?
Right. Okay. Yeah. Yeah. I mean, well, takeaway message from our result is that the ancient viruses from the past can create dramatic ecological change. Even if this was somehow rare in our simulation, then you have to think at this rarity in the perspective of the huge number of organisms that are released every year. So we simulated just one invasion by one virus, but with what is happening now is that you actually have runoffs of continuous runoff of organisms, since the permafrost is melting at amazing rate, and models predict that we might lose more than 40% of permafrost by the end of the century. So that means that so in our experiment, we basically demonstrated that these organisms might not only survive, but they might dramatically change the diversity and the composition of the bacterial community which are there. So all of these, I understand, might seem quite absurd, but the concrete implication of this is that since the permafrost has been already melting for some time and is melting faster and faster, we might already have a huge amount of novel ecological settings, so novel ecological microbial communities modified by the presence of these ancient pathogens, not just because of the presence of these pathogens, but also because of their impact. So they're not just different because those pathogens are there. So we do not have just the addition of these pathogens, but we have actually the addition of these pathogens plus their effect and the changes that they create in the novel community. So we might have all these novel microbial community. And this what in the end, and this is why we mentioned the potential risk also for human health. So whenever we create this kind of novel ecological settings, we also create novel emerging risks, because we can have, for instance, novel risks of the over of those viruses to animals and potential emergence of zoonotic diseases. And the fact that the release of ancient viruses is somehow random, and it might be, of course, different in different regions, might also means that we might have not just like the same novel setting emerging here and there, but we might have a very large set of very different novel ecological settings. And each one of those novel settings might be associated to different risks, to different possibilities. So it's like we are creating a large set of potential sort of natural laboratories where ancient viruses are interacting with modern bacteria, creating potentially novel elements of risk. So what our study shows is the ecological mechanism, and really from some theoretical perspective, but it's also provide quite strong evidence that the ecological risk and the potential extension of this ecological risk also to other kinds of threats, also to human health, might be real. So what we hope with our study is to actually encourage scientists to have a closer look at those novel ecological settings and to study them not just in terms of like single organism. So it's of course interesting to know that we can revive an organism which is 50,000 years old. That's clearly
right. Okay. How can people find out more about your research? Where can they go?
They can have a look at. I have a ResearchGate page where all my research is available. And last year I published a book with Springer, which is called Hidden Pathways to Extinction, where I discussed a lot of my research on how and why ecological interactions are fundamental in the global change crisis.
All right, very good, Giovanni. Thank you for coming on the podcast and explaining. I appreciate it.
Thank you so much. It was really nice to have this opportunity.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.